This is it, folks. Your world is about to change. We'll be tracking features on the ground and matching it to a geometric model. Incredible results coming right up. We'll be using fisheye lenses. Yeah! Oh my god, that sounded fake. Don't worry, I will not be quitting my day job. Hey folks, so here's my geometric model. I have created one of the most accurate geometric models, and I will curve fit it with the imagery. And let's see what we're going to get. In previous videos, I've used commercial photogrammetry software, but we don't know what's under the hood. So here I am manually going to show you how it's done. So I have a file here and I'm copying photo by photo in a sequence. And then I'm manually tracking this beach, the Nueva Beach, the Red Sea crossing. I'm obsessed with it now. So there you go. I have a layer called track and I put all the dots on there. And here I'm just verifying by clicking through all the layers. And I'll be adding more layers. There'll be, quite a few there. As you can see, this is quite a laborious process. I added 28 layers and now I am verifying, making sure I haven't missed a point. So I'll be clicking the visibility on each layer to make sure that the dots correspond with where the beach should be in that frame. Here you go, layer 19, 18, 17, 16, 15. I sped up the clip here at 300. I don't work that quick. So there we go. Nueva Beach goes through all the red dots as I enable visibility on the different layers. And yeah, I didn't go any farther because it's hard to see. Now I'm putting some circles around the dots so I could see where they're at when I zoom out. And here I am adding labels with the number of pixels, okay, from the bottom. So I will use those values. Now I'm adding a line just to see if they're straight, and they're pretty straight. Wow. Okay, so here's the goods. So I created a spreadsheet with calculations. Don't worry, I'll break this down real quick. So on the left, we have a geometric model. Okay, very generic. I'm assuming a spherical Earth. The ISS is up there, travels at a velocity v, etc. The calculations are very basic, okay? The images were taken every 5 seconds. We know the velocity, so we can calculate an arc length S, okay, from the nadir point right below the ISS, okay? And as time goes on, we calculate larger and larger arc length, and then we turn that into an angle theta from the center of the Earth, okay? And then based on that, we calculate the X and Y coordinates relative to the ISS. Okay, so now we are in a frame of reference attached to the ISS. And lastly, we turn those XY coordinates into angle alpha relative to the vertical. Okay, so that's the output that we will compare with what we get from the images. In the center of the spreadsheet, we have the photogrammetry analysis results, okay? And the output, again, is this angle phi relative to the same vertical. So the process is very simple. We're just going to match the model predictions to observations. And lastly, to help us match the model, I plot the angle error and I constrain the closest point to the other one. Okay, that's why it says 0, 0. That's the pivot point. So we'll be varying parameters to try to match what we see in the photos with proper parameters of the geometric model. See if we can do it. But right now, as you can see, for a radius of 4,000, we have a problem. It is not matched. There's quite a difference. Uh-oh, we have a problem. Help me, C-3PO.
I'm going to regret this. Are you sure this thing is safe? How did we get into this mess? We seem to be made to suffer. It's our lot in life.
Yes, it is our lot in life, C-3PO. It is. Well, that's all fun and games, but is this data even accurate? Let's take a closer look. The information for the nadir point comes from the gateway to the astronaut photography, from where I got the photo. So you can see it right there, and the altitude as well. And we'll use Google Earth to measure that distance from the nadir to Nuweiba Beach. Okay, and it's about 439 miles. So let's go ahead and try to match these two models and see what we get. We'll play with the radius of the Earth and see if we can do it. Okay, let's try and find a solution. So 4,000 doesn't work. Let's try 8,000. Oh, it goes in the right direction. It's starting to flatten. Let's go higher to 15,000. Ooh, seems to be going in the right direction. Let's go even higher, 50,000. Oh, it's going down. This is good news. Let's try 100,000 miles. Very suspicious here. Yeah, it doesn't seem like we can. Now, if I change the focal length to 28, forget it. It's even worse. So that's why I believe there is a 2x teleconverter on there. So what's going on here? How come we cannot match the points? There's quite a bit of error. And so let's try to mess with some other values, okay? If we mess with this one, it changes a little bit. I don't want to mess with it. I think I'm going to leave it at that value. See, look at that. It just gets wonky. So I suspect something else is going on. Let's change radius back to 50,000. So the curve comes up. Now let's mess with the velocity. Ooh, that comes down. See, ooh, that improved a lot. Whoa, I think we found a parameter here. That's very responsive. Wow, you gotta be kidding me here. Whoa, look at that, folks. Wow. So the velocity is not accurate? Wow. Look at this value, folks. I got 0 error. Look at the pixel errors. Oh my God, this is great. So why is the velocity higher? That's kind of curious. Well, the first thing that came to mind is there may be a vector addition of velocities, right? The closing velocity could be higher. The ISS is going 17,800 miles per hour or so. That's the quoted number, based on orbital mechanics, etc. Of course, that number could be bogus. And then obviously the Earth's surface has a velocity as well. But if the Earth is larger, well, that surface velocity would be higher as well. Now, the other intriguing concept to keep in the back of your heads is, what if time slows down on the ISS? That would have the same effect, but we'll come back to this. Now notice towards the farther points how it droops down. That's the effect of refraction, folks. That's not lens distortion, right? Because the lenses are corrected. Plus, those points are not even close to the edge of the lens. So it appears we are well corrected for about 10 to 14 points from the bottom. So that takes us almost to the center of the photo. Wow. So who's to blame for this refraction? As astronomers and surveyors well know, looking down at steep angles to the atmospheric gradient is the best way to measure angles. So which way is light bending? Let's take a look at the spreadsheet. Notice the angle error. Towards the bottom, the numbers are negative. That's because we're subtracting phi1 minus the other one. Okay, and so phi1 is smaller. So we have to visualize this. So here's the incredible result that comes out of this analysis, folks. Not only is the Earth way bigger than I thought, this is kind of a shocker, greater than 50,000 miles. Wow! That's like at least 10 times bigger than the accepted value. But refraction is upwards, like I always suspected, because if you follow any of the experiments that government labs do on and universities on slowing down light, they have very low pressures and cold temperatures mimicking outer space, okay? And it kind of stands to reason that, yeah, light should be propagating slower in that environment, okay? And so that's why light kind of curves up. The face front curves up, all right? So that makes perfect sense to me. I hope it does to you as well. And there you have it, folks, the world's best Earth curvature calculator.
You did it! Congratulations!
Thanks for watching, guys. Stay flat out there.